All right, good morning, class. Hope you all are doing well. Just to give you a heads up, last 24 hours have been kind of crazy. Both my wife and my daughter are both sick. So we're going to take them in to get COVID testing later on today. So I thought I was going to be canceling class because I thought I'd be taking my daughter in this morning. But the appointment's a little later this morning, so I'm going to go ahead and hold class. But with that said, I'm a little less prepared for class than I normally am because I've just been so busy the last day and a half. So we'll get through it, and hopefully what we do today will be enough to get you through your homework. But the homework solutions, you'll have to just give me some time to see how things go today. All right, any questions over law of cosines from last time? No? Okay, I got those homework solutions put up. I did almost all the problems. I skipped a few, but I think I did enough for you to get through it. So if there are no questions, we're going to continue on. We're actually on our schedule. We're on track to be doing vectors today. And the chapter, we're switching chapters. We're going to chapter 10 and we're skipping all the way to section 4. So really these last sections that we're going to cover are just kind of like these ancillary topics that we just want to make sure you've seen. That's why we're kind of going to jump around. We're going to go 10.4, 10.5, 10.1, 11.2, 11.3. So the core of what this course is about is what we've done up to this point, and now we're just going to kind of knock out these other topics. Okay, so we're going to do vectors now. Like I said, I wasn't quite prepared to do vectors today, but I do vectors in my Cal 3 class. On the second day of class, we do a review of vectors. So I'm just going to use my lecture notes from Cal 3 for today's lecture. And so it says 10.4 here, but when I bring up these notes, it's going to say chapter 10, section 2, because that's where it appears in the calculus textbook. So just ignore that it says 10.2. And then also when I'm doing my Cal 3 class, we do vectors in both 2-dimensional space and 3-dimensional space. So my notes have both. I'm going to not cover the 3-dimensional stuff. I'm just going to do the 2-dimensional stuff because that's what's in the pre-cal class. All right. So let's get started. Vectors. Vectors are something you may have seen if you've taken a physics class. The idea of a vector is that let's say you want to take this book here, and let's say I want to kind of just like grab it and drag it across the table. Well, when I'm dragging it, I'm applying a force to the book, okay, and I can have some certain angle that I'm pulling it at. So I could pull it from here and drag it across, okay, or I could kind of lower that angle down and I could pull it like this, okay. But as I'm moving the book is moving, my arm is moving, and you can try and imagine that the force that I'm applying is a force that is in this direction of my arm. And as I'm moving it, my arm is moving, but the force is always the same as I'm pulling it, okay? So physically, we want a way to represent this force and allow it to move around through the space without the force ever changing. So we need something geometrically that represents something like a force that can move around wherever we want it, but still be the same thing. So I guess the thing you have to kind of wrap your head around is if I move my arm through space, then my arm is at different points in space. But I want the force to be something that it doesn't matter where I am. No matter where I am in the space, this force still stays the same. Okay, so that's kind of like one of the motivating ideas behind a vector. So let's get into the definition, and as we get to the definition, I think you'll start to see how this comes to light. Okay, this idea of the force. Okay, so let me make this a little bigger. So vectors are objects that have two main properties. All right, so all vectors have these two main properties. First, they have what's called a magnitude. Now, we also call that the length or the norm of the vector. Okay, so a vector, right now, a vector in your mind should be something very general. Okay, and I'm telling you that all vectors should have a magnitude, all right, which represents the length of it. And then the other thing that a vector should have is a direction. Okay, so a vector is just simply something that has a magnitude and a direction. And that's just which way it points, right? So the geometric concept of a vector, and now do y'all see here where I put here R2? Okay, that just means, you know, in the XY plane. Okay, so when you're in the XY plane in two-dimensional space, we call that R2, right? So the geometric concept of a vector on a flat sheet of paper is that you have this, it's almost like an arrow, okay? And it can point anywhere you want it to point, all right? And it starts somewhere and stops somewhere. And so we call this the tip of the vector. We call this the tail of the vector. This will come up in the notes again. I'll label these things.
I have a question.
Yes.
So if it's in the XY plane, it's R2. Does that mean that if it's in like the XYZ plane, is it R3?
Yes, R3 would represent three-dimensional space, which is generally hard to draw because when you try and draw a three-dimensional space on a flat sheet of paper, it's inherently difficult. So like one way we can do it is you draw like this, and then the ground is the XY, and then the Z comes up here, and that would be referred to as R3. Now we're not going to do R3, okay? We're not touching it here today, but that's what R3 would mean, three-dimensional space. Okay, so there's a vector in R2, right? I can move it anywhere I want. Doesn't matter where it is, change its length and direction. Now, when we say direction, we have to be clear on something. So let me move this vector. Let me start it at the origin. It doesn't have to start at the origin, but let's just put it here. Then if we're talking about its length, the length is from here to here, right? That would be its magnitude. I'm just going to put mag. That's its magnitude, is how long it is. And then the direction, okay, the direction, we need to have some way of orienting the direction. So what we do is we always consider going out the positive direction on the x-axis as being 0 degrees. And then we measure from here to here, and that would be the angle that it points. So whatever this angle is, theta, okay, would be its direction. So this vector would have a magnitude of this length, whatever it is, and the direction would be this angle theta. Now, what's important about that is if I move, let me move this vector. If I move this up to here, I moved it up 2 spaces. If I move this up 2 spaces, then that vector would have the same magnitude, and it would also have the same direction, because we would have to imagine extending a line out this way and then measuring that angle, and that would also be theta, as long as those were parallel, okay? So again, length, direction are the main 2 characteristics of a vector. Okay, so I'm not going to do the 3-dimensional vector. So some things about vector language in notation. When we draw a vector, okay, I said this was called the tip and this was called the tail. There's another term that we use for the tip. It's called the terminal point. And then this point right here is called the initial point. So you could look at this as being a point, and this as being a point, 2 points on a plane. But the vector is the arrow that goes from one point to the other. So it starts here, the initial meaning the starting point, and then the terminal meaning the stopping point. So if somebody gives you just 2 points, and says, hey, what's the vector between those 2 points? That's not enough information for you, because the vector between 2 points could be this vector going from here to here, or it could be the vector that went the other way. And those 2 vectors are not the same. Okay, the black vector has an initial point here and a terminal point here, but the blue vector has this is the initial point and this is the terminal point. Okay, so it's very important that you understand that the vector has a direction. So it's not just a line segment. It's not just a line segment connecting 2 points. It's what we call a directed line segment. Okay, now the other thing is we need to name the vector, right? We need to give it a name. So the common name for it is to call it V for vector, right? But we need to let you know that we're talking about a vector. So above the vector, above the V, we put this, what it is an arrow like that. And we're cutting off the bottom, sorry. It's an arrow. And then we're just cutting off the bottom piece right there like that. And that's what we put above the letter V. And that lets you know I'm talking about a vector. And so why would that be important? Well, if I write X, we all know X to be like a variable, right? X, like in college algebra, X is a variable. We solve equations that have X in them. X is, when we talk about X, we are usually solving for X to, where X is a number, right? Like solve 2x plus 1 equals 5, right? We solve this and we would get X is 2. Our answer is a number, right? If I write the letter V, then V is just like X, and I could write an equation with V, 2V plus 1 equals 5, and then you can solve for V, and V is 2. But if you write V with that little half arrow above it, now you're not talking about a variable where the answer is a number. Like, it would be impossible for me to write this down and expect you to get an answer like V equals 2, because vectors are not numbers. So this is not possible. So it's very important for you to understand that the arrow above it is what lets you know you're talking about a vector. Now, in most textbooks, they don't use the arrow. In most textbooks, what they do is they put a bold, they make the letter bold. I'll show you. I'm going to bring up your textbook. Let me see here. Let me back it up. Okay, so here we go. Here's the textbook. And let me get back to the beginning of the section. One more page. Okay, no, still one more page. Okay, so here we go. In the textbook, see how they use bold? V equals W, or V plus W equals W plus V. So anytime you see a bold letter, that means it's a vector. So they don't use the arrow. Now, the reason we use the arrow is because when we're writing, it's hard for us to write bold, right? That's a difficult thing for us to do when we're writing with a pencil. So we use the little arrow instead. All right, any questions on that? Just the idea of tip, tail, bold, naming it. Okay, now equivalent vectors. This is a very important idea. Two vectors are said to be equivalent or equal to one another if they have the same magnitude and direction. The position does not matter. So I'm going to show you two vectors here. Here's a black vector. Okay, let's call that vector V. Okay. Now here comes another vector. Oh, I'm sorry. V's going to stay. Let me get rid of that. Okay, we'll make the blue one V. And then we'll move the black one around. So if I move this black one, do you see that this black one, no matter where I move it, as long as I don't change how long it is, and as long as I keep it parallel to the other one, then these two vectors are equivalent. So let's call this black one, let's see, what we normally like to use, the letters we use for vectors, V for vector, and then U is another one we use, U. We like to use W also. So we like to stay away from X, Y, Z. We like to stay away from A, B, C, D. So X, Y, Z is what we usually use when we're solving equations. A, B, C is usually what we use to represent constants. Theta, alpha, beta is usually for angles. V, U, W, those are usually reserved for vectors. Now, there's nothing that says you have to, but that's the normal convention that we use when we're doing math, all right? So these two vectors are equivalent, which means I could write that the vector U equals the vector V. And this is the idea that I was saying when I'm saying I'm dragging this book across the table. I have this force that's coming in the direction of my arm, and how big this vector is depends on how hard I'm pulling on the book. If I pull really hard, then that vector, the way we represent that is by making the vector very long. If I don't pull very hard and I just barely pull, then the vector will be very small, but still point in that direction. But as long as I keep the force constant and I just pull, then you can kind of see that, I know this pen doesn't show up on the camera very good, but you can see that the vector is the same as I'm moving it through the space. So this is always the same vector. You don't have to worry about the fact that you're moving around. What this note, this very important note is telling us, what makes two vectors equivalent? Well, they just have to have the same direction and same magnitude. Okay, so now, how do we determine a vector in two-dimensional space if we're given 2 points? So this is that idea I just told you a second ago. If we have 2 points, A and B, we have one vector that goes from A to B. And then we have another vector that would go the opposite direction from B to A. So first, some notation. Let's look at the vector that goes from A to B. So if we go from A to B, okay, let's talk about that first. Well, the first thing is that A has to have an X coordinate. I'm going to call it X1 and Y1, right? Because A is a point. And then B also has to have an X coordinate, X2, and then Y2. So those are 2 standard points, the way we've looked at points our whole lives. If we want to find the vector that goes from A to B, the first thing we're going to do is we're going to notate it like this. We're going to go AB with the vector symbol across it. Okay, so that just lets you know I'm about to give you a vector. I'm about to write down a vector that goes from A to B. And the way we write it is this. We use what's called an angled bracket. Okay, so this is a parenthesis, right? This is a brace. This is a bracket, and this is called an angled bracket. So we write an angled bracket, and then what we do to figure out, and this is just notation how we write a vector, is we take this X coordinate, X2, we subtract X1, then we put a comma, and then we do the same thing for the Y coordinates, Y2 minus Y1, angle bracket like that. That's how we would represent the vector that goes from A to B. Now, if we wanted to go the other way, from B to A, then we would write B, A, vector equals angled bracket. And now we reverse the direction. So since we're going from the B to the A, we start with the X coordinate here and we subtract that one. So it's X1 minus X2, and then it'll be Y1 minus Y2, like that. Now I'm going to copy this down and we're going to do an example just to make sure that you understand how to do that. So as an example, hold on a second, I have to close this and reopen it. Okay, example, find the vector from the point 5, 7 to -3, -1. Okay, so this is all about just notation, all right? So these are 2 points. You need to realize these are both points, right? They're points because they have parentheses around them. And so if I call this point, let's say we call it A and this one B, then we're trying to find the vector from A to the vector from the point A to the point B. Okay, so who wants to tell me what calculation I'm going to do in here? So what comes first?
So you would, so I'm calling -3, -1. -3 would be x2, and then -1 would be y2. So I'd have -3, you'd have -3 -5, comma, -1 -7.
Yes. And you do not have an option there in terms of the order. You don't get to choose. You can't say, oh, I'll do -3 and take away 5, -1 take away 7, or I'll just do it the other way, 5 minus -3, 7 minus negative. No, you don't get a choice. If you're going from A to B, you always start with these and subtract these from them. So we still need to figure out what that is. That's the vector -8, -8. Okay. Now, let me graph this for us, just so we can see what this really looked like. I'm going to change this to a grid. So if we had started out in the XY plane, I'm going to have to really try and squeeze this in here. We started with 2 points, 5, 7, 1, 2, 3, 4, 5, 6, 7. Sorry, 1, 2, 3, 4, 5, 6, 7 there. So we went out 1, 2, 3, 4, 5. Here's 5. Went up 7. Here's 7. Okay, so that's the point A. Feel like I'm gonna sneeze. Oh, sorry, it came out of nowhere. Okay, the other point is -3, -1. That's right here. That's point B. Do you ever sneeze and see these like little white tracers going everywhere? Ooh, it looks weird. Okay, so we're trying to find the vector that goes from A to B. So we're trying to find that vector. And what we found was -8, -8, right? So -8, -8. So I would like us now to think of this vector as almost like a point for right now. If we were to start at 0, 0, let's say we start at 0, and I told you to go to the left 8 and down 8. You go to the left 1, 2, 3, 4, 5, 6, 7, 8, down 8, 1, 2, 3, 2, 3, 4, 5, 6, 7, 8. If I drew that point there and connected a vector from here to here, do you see this vector AB? Do you see that this has the same length in the same direction as this vector? So this is the vector AB, but so is this, right? And I can move this anywhere I want and it would be the same. So I guess the thing I want you to understand is that if somebody gives you 2 points and you draw a vector between them, yes, the vector connecting those 2 points is the correct answer, but you're allowed to move that around now anywhere you want. So the 2 points, all they do is establish the vector, and then you can move it anywhere. All right? Okay. Any questions on this? It's making sense so far? Okay. So this is what I just gave. I'm sorry, this was the formula I just gave you right here. If you have 2 points, A is x1, y1, B is x2, y2, then the vector from A to B is this one. The vector from B to A is the other way around. Do you want me to do the other way around here, or are you happy with just doing one of these? Do you want to go vector B to A, or is it pretty self-explanatory there? Don't care?
I think it's pretty self-explanatory.
Okay. Can anyone just tell me what the answer would be?
If we
If
went,
I asked you for the vector from B to A instead, what that answer would be?
Using those two same points.
It's the, yeah, using these two same points.
it would be 8, positive 8.
It'd be 8, 8
Yeah.
instead of -8, -8. So it would be almost the same thing, except the signs change. Right, because you're reversing the way you do it. You do 5 take away -3, that's 5 plus 3, that's 8. Then you do 7 take away -1, that's 7 plus 1, that's 8. So the fact that these would both be almost the same, but off by a sign, is actually a property, but we'll talk about that in a minute. Oops. Okay, let's get back to the notes. So we're not doing 3-dimensional, so I'm skipping this note. And then this was an example that I normally do in my Cal 3 class, but it's 3-dimensional. We did an example in 2 dimensions, so we're skipping that. Now, a very important vector. It's called the 0 vector. And I need to first get rid of that. Okay, that's 3-dimensional. The 0 vector is a vector that has 0 and 0 inside the angle brackets. And we represent it with a 0 with a little half arrow above it. Now, that may seem like obvious, but it's important. If I write this down, we all understand this, the number 0, we all understand that right now in this class and previous classes to be on the number line. It's the number, you know, here's -1, here's 1. 0 is that, right? That's what it represents to us, you know, before today. But now I'm telling you there's something called the 0 vector. And what it is a vector, so I have to put an angle bracket over it, where each of the numbers inside the angle brackets are zeros. These two things are not the same thing, all right? The number 0 and the vector 0 are not even the same objects. It's like a cat and a dog. The number 0 is a number, right? That's a cat. And the vector 0 is a dog, okay? It's a vector. So can't confuse these two things, all right? Now, the weird thing about the 0 vector is this. There's something very strange and unique to the 0 vector that's different than all other vectors. First of all, what's the magnitude of this thing? How long is it?
It's
What
not
do you
infinite.
think? What's that?
Is it infinite?
Okay, you know how we drew a vector a second ago and we started at the origin and then we said it was -8, -8. So we went to left 8, down 8, and we drew that vector,
Yes, sir.
right? Okay, so if I tell you to start at the origin and then go 0, 0, you're still going to be at the origin, aren't you?
Yes, sir.
So how long would that be?
Nothing.
Nothing, right?
You wouldn't have
The
a
magnitude of this would be 0, okay? Okay, so all vectors must have a magnitude. They must have a magnitude and a direction. The 0 vector has a 0 magnitude, okay? It has no length to it. That's okay. I mean, you could have a length of 1 or 2 or whatever, or 0, that's okay. So far it has a magnitude, it's just a weird magnitude. But what about a direction? This is the part that's weird. How about the direction of this vector? Well, I mean, it's not pointed anywhere, right? Because you don't have an arrow. It's just there. So it has none. No direction. And that's the only vector that behaves that way. Okay, so this is the exception to the rule. I said in the very beginning, all vectors must have a magnitude and direction. There should have been a little asterisk next to that that said, except the zero vector. The zero vector, we're okay with the fact that it doesn't have a direction, all right? It's an important vector. You'll see how we can use the zero vector later, but we just have to introduce it first, okay? Questions? Zero vector. Now, some more language. When you write a vector with this little V notation here, right? Two-dimensional vector. I said to use an angle bracket, then you put some number in here and then comma and then some other number here. Those two numbers we put in here, V, in this case, I'm calling it V1 and V2, are what we call the components of the vector. It's the first time I've used this language. The V1, the first one here, is called the X component. And then the V2 is called the Y component. And I say, don't confuse that with coordinates. And what I mean is, if you go back to when you were learning about points, right? Points. If I give you the point here, let's say 3, and then go up 2, and you draw a point, then that would be the point 3, 2. And we would say that 3 is the X coordinate and 2 is the Y coordinate. That's the way we deal with points. When we're dealing with vectors, we don't use coordinates so we don't confuse them. And we use the word components instead. Now, three-dimensional, we're not going to worry about. Okay, so this is just a language thing. Components, first time we're seeing this. Questions? All right, we're moving on. Vector addition. Okay, so when you think about the things that you've learned, when go back, take yourself back to elementary school, right? You're learning about numbers. So hey, there's these things called numbers, and then you start learning how to add numbers, right? You learn how to subtract numbers. You learn how to multiply and divide numbers, right? So there's like 4 arithmetic operations that we use with numbers, right? Those are the 4 arithmetic things. When you get a calculator, it has plus, minus, multiply, divide. Those are the basic operations between numbers. Well, with vectors, we want to know, are there ways to do those 4 operations? Can you add 2 vectors together? Can you subtract 2 vectors? Can you multiply 2 vectors? Can you divide 2 vectors? Does it make sense? What you wind up learning is that, yes, you can add 2 vectors together. It's actually pretty easy to do. Subtraction's pretty easy to do also. But when it comes to multiplication of vectors, there's actually 2 different types of multiplication. There's not just one, there's 2. And that's not, we don't have the same thing with numbers, right? Like when I ask you, hey, what's 4 times 3? You don't respond to me and say, well, which multiplication do you want me to use, right? There's only one multiplication. 4 times 3 is 12. But with vectors, if you're ever asked to multiply them, there's actually 2 types of multiplication. One of them is called the dot product, and the other one's called the cross product. So we in this class are only going to talk about the dot product, but I'm just trying to kind of lead you into this idea that with vectors, things change. Things become a little different than they were with numbers. Okay, so here we go. Let's add 2 vectors together and let's look at it geometrically first. Okay, we're going to look at the geometric idea of adding 2 vectors. And when we look at it geometrically, what we're going to determine is this thing called the Parallelogram Law. And hopefully you'll see it as I show you the picture. So how do we add 2 vectors together? When we add 2 vectors together, and this doesn't matter if we're in 2-dimensional or 3-dimensional space, even though we're not looking at 3. All we do is we take the tail of one of the vectors and paste it to the tip of the other. That's it. You may do this in reverse also. It doesn't matter which one you pick. You just go tip to tail, tail to tip, doesn't matter. Either way, the resultant vector is the vector from the tail of the first one you chose to the tip of the second one. Okay, so let me show you this with the picture here. Okay, so I have two vectors here, right? I have the red vector, which is the vector v. It obviously has a length and it has a direction, right? The v one does. The u one has its own length and it has its own direction. If I want to add these together, all I have to do is move them around to where the tip of one hits the tail of the other one. So let me move you. I'm going to move you the other way. So what I'm trying to do is I'm trying to get the tail of this one to touch the tip of this one. So I need to move it up, right? There we go. Okay. So I have taken this red one, I've taken its tip and attached it to the tail of this vector u. And then I drew a vector here. So let's try and understand what's going on here. It says that either way you do it, no matter how you do it, the resultant vector, that's the answer, is the vector that goes from the tail of the first one to the tip of the second one. So if we look at this, this is the tail of the first, right? So we start here, tail of the first one goes here, and then we attached it, and then it went back to here. This is the tip of the second one. The resultant vector is the vector that connects those two together, which is the vector that goes across here like this. And that is what v plus u is. Do you see? This is v. We added u, and so the result, I just called it v plus u and put a vector over it so you could understand that that's the result of what you get when you add the two vectors together.
How do you determine the direction?
Well, the direction is because we start here at the tail of this one and go to the tip of that one. So that's why the arrow points that direction.
Okay. That makes sense.
Okay, I'm going to leave that there. I'm going to leave all this here, but now I'm going to move that blue vector back to where it started. Couldn't I have done it the other way around though? Couldn't I have, like, just left the u and moved the v instead? So why don't we just leave u here? Let's attach the tip of this to the tail of the red one. So I need to move the red one. So I'm up. I want to move it to the left a little bit. There we go. And I need to move it not up. I need to come down just a little bit. And then, okay. So when I put these together, I'm about to do it. It's the resultant vector should be the vector that goes from the tail of the first to the tip of the second one. So I'm going to move it down, and there it is, from here to here. You'll see it starts here at the tail of the first and ends at the tip of the second one. So it's this vector from here to here. Now, do y'all see what we have? Y'all see that this vector and this vector are exactly the same? Same length, same direction. But this one I got by doing the u and then adding the v. So I have over here that we did the u and added the v, and that was another vector, but it looks like these two are equal, right? Looks like they're equal vectors. This one down here, I'm gonna put it here. Looks like those two vectors are the same, right? Okay, I'm gonna take the vector. Oh, I'm not doing that. I'm gonna take the vectors back to where they started. Okay, here is the original position of both vectors. So this idea of what's called the parallelogram law, right? This parallelogram law. If you look at where we were when we started here, right? If we look at this, if you were to connect the two resultant vectors together, you get this parallelogram. And so that's the idea of the parallelogram law. Says basically that if you take any two vectors and add them together, no matter which way you do it, it would form almost like this parallelogram. It's not super important. It's just a geometric kind of, result. So yeah, that's it. That's what vector addition looks like geometrically. tip to tail to tip, draw a new vector, you're done. Let's do an example. These examples are hard to do because you almost need like graph paper to do this, but we'll try, okay? We'll try our best here. So I'm going to put a grid here for us. So there's our XY plane. I'm going to draw a vector. It's going to go here. That. Okay, I'm going to call that vector U. And then I'm going to draw another vector, which is going to go here. Let me make it a little bit different. Let me go. Jeez, terrible. Okay, I'm going to call that vector V. Okay, there we go. So what I'd like for us to do is I'd like for us to find, and what I mean by that is draw, okay, U plus V. And then that's part A, and then let's find V plus U. So let's start with U plus V. So I'm gonna take U, and I'm going to take the tip of U and attach it to the tail of V, which means I'm going to make a copy of this. And then I'm going to move it where the tail and tip touch, just like that. Okay. The resultant vector is the vector that goes from the tail of the first one to the tip of that one. So it should be the vector that goes from here to there. That should be U plus V. Questions? If we do V plus U, I'm going to leave V alone. I'm going to make a copy of, U. See if this works. Yes, good, that worked. And then I'm going to move it to where the tip of V touches the tail of U. Like that. So that one was U. And now the resultant vector starts at the tail of the first one to the tip of the second one. There it is. That's V plus U. And do you see that both of these are exactly the same vectors? So this would be hard to do on a piece of paper yourself because I did copy paste, which made it easy for me, but you would just try your best, okay? All right, I'm going to move on if that's okay with you. So that was basically a couple of examples of that. But all right, now, what about vector addition without pictures? How do we do vector addition by hand? And I have good news. It's really easy. Okay, so we're going to ignore this. If you have two vectors given to you, let's say U, and we'll call it U1 and U2. So U1 is the X component of U, U2 is the Y component of U. Then we have another vector V, which V1 is the X component of V, and V2 is the Y component of V. Then to add the two vectors together, all you do is add the components. So you take U1 plus V1 and put those in here, and then go comma, and then the U2 plus V2. And that's it. Very simple to add vectors. Subtraction works the same way. If you have U and you want to take away V, then you do subtraction inside. So let me copy this. You're probably sitting there wondering, like, maybe like, when is this going to get hard? It's going to get a little weird. Don't worry. We just got to make sure we get the basics out of the way here. Okay, so I'd like for us to do an example here. So as an example, I want us to take if u is equal to the vector -2, 4, and v is equal to the vector 1, -3, I want us to find u plus b, and then let's find v plus u, and then let's find u minus v, and then we'll find v minus u. This is going to be just quick, very quick arithmetic. Who wants to give me u plus v? The answer is a vector, right? So if I add two vectors, all I do is add their components.
It would be -1, 1, right?
-1, 1. So all you're doing there is adding. You're doing -2, add 1, 4, add -3, which gives you this. What about v plus u?
Wouldn't it be the same?
Same exact thing, right? Because all you're doing is adding the components. Okay. So add them up, you'll get -1, 1. Now, be careful here. U minus v. Now you're subtracting. And this, the order matters. If we're doing the
-3,
u,
1, right?
yeah, so what we do is, since we're doing u minus v, we start with u, we take -2, and this time we subtract the 1 from here. And then it'll be the 4, and then we will subtract the -3, like that. And this will give us a vector -3, 7.
Yes.
And then we'll do the other one. Now the order changes. You're doing v, take away the u. So you start with the v's and take away the u. So 1, take away -2. And then -3, take away 4.
It'd be 3, -7, wouldn't it?
Yeah, it's going to be 3, -7. So it's the opposite. Okay, so I want to show this to you visually because there's something really kind of interesting that happens here. Watch. My calculus students seem to have trouble with this sometimes. Okay, so I'm gonna just show you what I'm gonna draw you here, okay? And I'm gonna draw it by starting at the origin and just moving 2 to the left and up 4. So here's -2 and up 4. Here's 4. So this could represent the vector u. Do you all agree? I can move it anywhere I want, but if I start at the origin, go to the left 2 and up 4, that's u. V, I could do to the right 1, down 3. Here we go. Those almost look like they're on the same line, but they're not. Okay, there's v. Now, let's look at the u plus v first. U plus v. So I leave u alone. I make a copy of v. And then I attach it right like this. Okay. And do you see that if we start at u here, follow it through, there's u, and then here's v. I end here, and that vector goes from here to here now. That's u plus v. And is that the vector -1, 1? It is, right? It's the vector -1, 1. Okay. Well, that's nice. I'm going to make another copy down here. Okay, let me get that out of here. See if I can do this without erasing everything. Shit. Okay, I just erased everything. See if I can do this. All right, let's do. I might have to draw this over because it might be too hard to fit it on there. Okay, so let me put u here again. U goes to the left 2 and up 4. So here's u. And then v went to the right 1, down 3. Here's v. And I want us to look at what u minus v was. What was our answer to u minus v? Negative 3, 7, right? Negative 3, 7. Let's see where that is. Negative 3 and then up 7. 1, 2, 3, 4, 5, 6, 7. It's right there. So negative 3, 7 is this vector that goes from here to here. That's what u minus v looks like. So how do I get that from here? Like if I start with u and subtract v, how am I winding up here? Can y'all see what I'm doing to get up there? Take this vector. How can I attach this to u to end up there? Don't I have to put it like this, but change its direction? Like flip it over, right? I have to actually like take the v, but don't put v, put the opposite of v, which is going the other way, which means like there to there. And the question becomes, is that what negative v looks like? Is negative v just that same vector pointed in the opposite direction? I don't know, maybe it is. That's what the next note's about. I just want us to think about that, that's all. Scalar multiplication of vectors. So if you're given a vector, v, and a scalar means just a number, then taking that number and multiplying it times v changes the shape of v. If the number that you pick to put in front, if the absolute value of it is bigger than 1, it's going to stretch the vector out. If the absolute value of that number is between 0 and 1, it's going to shrink the vector. And if the c is negative, it's going to flip the vector over and point it in the opposite direction. So let me show this to you first. So what we have here is the vector 3, 3. Okay, this is the vector 3, 3. So out 3, up 3. And what I'm going to do is I'm going to multiply it by some number c, and that's going to be this number here. So right now I'm just multiplying it by 1. So it's the same vector. But what happens if I multiply it times like 2? So here's v, the black vector. If I do 2 times v, I get a vector that points in the same direction but is twice as long. If I do 3 times v, it's the same direction, just 3 times as long. If I make the number in front less than 1, but greater than 0, like maybe like 0.5, now I have a vector that's in the same direction, but half as long. So do you see how the scalar multiple, the number in front of the vector, either stretches it out or shrinks it? Now, if I make a negative number, look what happens. So like negative 2, if I put negative 2 in front of this vector, it takes that vector, it doubles its length, and then it points it in the opposite direction. So that's what scalar multiplication is when it comes to vectors. Start with a vector, multiply it by a number in front. If the number is bigger than 1, it's going to stretch it. If it's between 0 and 1, it shrinks it. If it's negative, it flips it over. Now, how do you do scalar multiplication? Like by hand? If you're given the vector, which will have, an x component and a y component, and then you put a number in front, then all it does is you just almost like distribute that number through to both of the components. So I'll show you that with an example. How about you try this on your own? I mean, this stuff is not too difficult. If u is equal to the vector -3, 4, and the vector v is the vector 2, let's say 5, I want you to find, part A, I want you to find 2u, then I want you to find -3v, and then I want you to find 2u minus 3v. See if you can figure that out on your own with what I just gave you. If I'm asking you to put 2 in front of U, how does that work? Do y'all need the note? I can give you the note if you need this. This shows you how to do vector multiplication.
It'd be -6, 8, wouldn't it?
Yeah, I'm gonna let everyone do that. Y'all figure it out. Try and figure out what this is, try and figure out what this is, and then try and figure out what that final thing is. I'll give everyone a few minutes. I'm just writing these down. I'm not speaking or anything. Okay. Does anybody have a question about the first two? Okay, what about the last one? How did y'all kind of visualize that one? Because that, I mean, not visualize, but how did you deal with this? Because this is 2u, which you already found, right? And then you're supposed to subtract 3v, but this is minus 3v. So how did you do that?
You change the coordinates to positive, correct?
What do you mean? Say again?
Like you change -6 and -15 positive.
Yeah, so I'm asking you to subtract 3v, right? Subtract 3v, right?
Right.
So
Yes.
there's 2 ways to look at this. This is really important. I intentionally gave this to you to see if I could trick you, okay? Everyone was able to find what 2u was. That's no problem. You just basically distribute a 2 to both of those. -3v, oh, you just multiply both those by -3. Boom, done. But this last one, there's 2 ways for you to look at it. One way is this. Well, take 2u. Okay, now what's 2u? We already found that, right? Didn't we? 2u, which is -6, 8. And then subtract from it 3 times v, not -3 times v, 3 times v. And so 3 times v would be 615. And then subtraction of 2 vectors, you just subtract the components. So you go -6, take away 6. And then you go 8, take away 15. And that would be equal to -12. What do we have there? -7. That's one way to do it. And I guess that way you're looking at 3v as not being the same as -3v. Okay, so you're not using this answer here. You're using this and multiplying by 3. Another way you can do it is to look at this as 2u plus -3v. because when you add a minus, it's the same as subtraction. And so this would become the 2u that you got here, negative 6, 8. But then you're adding to that the negative 3v, which you did get right here, negative 6, negative 15. And now that you're adding these two together, you just add the components, and that would give you the exact same thing. It'd be negative 6 plus negative 6, right? Negative 6 plus negative 6, and then you would have 8 plus negative 15. And that gives you the same answer. Any questions there? Still got a long way to go here. All right. Parallel vectors. Any two non-zero vectors are said to be parallel if they are scalar multiples of one another. That's all it means for two vectors to be parallel. They have to be scalar multiples of one another. This is a key word here, scalar multiples. So I'm going to give you a couple examples. So let's say I take the vector u, and I say that's the vector 2, negative 3. Then I give you a vector v, and I tell you that that vector is the vector 4, negative 6. Are these parallel?
No, but wouldn't they be almost in line with each other? Because it would be like taking vector u and multiplying it by 2.
Okay, so what you're telling me right now is that the vector v is just taking the vector u and multiplying it by 2?
Yes, sir.
Is that right? Does everyone see that? If I take this vector and multiply it by 2, it becomes 4, negative 6, right? Which is this vector. So v is equal to twice this. So then, Josh, doesn't that mean that you're scaling u? V is some scalar multiple of u?
Yep. Yes,
right?
sir.
And that's what it means to be parallel. So those two vectors are parallel vectors because one of them is a scalar multiple of the other. If you were to draw these, the vector 2, 3 would be to the right 2, negative 3, down 3 would be this vector. That would be u. And v would be out 4, down 6. That would be v. And you can see that they are parallel, right? They look parallel. So how about this? How about the vector? Let me give you another vector to consider. Look at the vector u is equal to, let's stick with 2, 3, 2, negative 3. And how about the vector w? How about that vector? I'll make it negative 6, 9. Are they parallel? Can you multiply this by something to get this?
Yes.
Yes. What can you multiply it by?
2 by negative 3.
Negative 3 and negative 3 here, right? So w is what you get when you take negative 3 and multiply it times u. And therefore, w is a scalar multiple of u. If we were to draw w on this graph, or over here, it would go to the left 6, 1, 2, 3, 4, 5, 6, and up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. We draw this point, and you would hopefully see that w is pointed in the opposite direction as u, right? But it is still in line with it. And that's what it means to be parallel. So that's something that students also forget or lose sight of. For vectors, parallel doesn't mean you have to be pointed in the same direction. Parallel just means you have to be somewhere on the line. If you were to connect, if you were to draw a line through here, any vector that's parallel would have to lie on that line somewhere. Okay, what about this? Is just one last thing. me clear this out of here. What if I give you u is equal to 2, 3, and v is equal to 4, 12? Are those parallel?
Yes.
Okay, so why do you think they're parallel?
Because you can get 2 to 4 and 3 to 12, but
Okay,
you're
how do you get 2 to 4? You have to multiply by what?
2
2. How do you get 3 to 12?
by 4.
By 4. Okay. To be a scalar multiple, these two numbers have to be the same number.
Okay.
Okay. So that's why I gave you this example, because just because you can get each one to turn into the other one doesn't mean that it works. It has to be the same number for both. So one way you could check this pretty easily is what you do is you take 4 and divide it by 2, and then take 12 and divide it by 3. And you get answers. Those have to be the same. If you look back on the previous examples, these aren't the same, right? So these are not parallel. If you look at the previous examples I did, if you do that same thing, when you do it, you'll get the same number when you do that division. Okay, we're moving on. All right, we finally get to the magnitude here. And when it comes to magnitude of vectors, the length of the vector, okay, if someone gives you a vector v1, v2, the length of it is notated with an absolute value. It looks like an absolute value sign around the vector. And it is found as follows. You do a calculation. So I'm going to show you where the calculation comes from because it's not that hard to see. If we take a vector, let's call this vector v, then that vector has as its components v1 and v2. v1 was the x component, v2 is the y component. If we want to know how long this is, let's call it L, okay, the length of this vector, that's from here to here, then we can imagine a right triangle. We can imagine that this distance would be the v1, the number right here, and this distance right here would be the v2. And then we just have Pythagorean. We know that v1 squared plus v2 squared must be capital L squared. And then we just take the square root on both sides. And that's what the length is. Now, we don't call it L, we use that notation. So do y'all see it's a very straightforward formula that we've used in the past, the Pythagorean, to be able to find the magnitude of a vector? There's no new math or anything here. So let's do, let's move to the next note, and then we'll do two and one here. Not gonna do that. Okay, yeah. All right, so hold on a second. Yeah, I want to do this in a different order. Yeah, you know what? I'll do an example now. Okay. So let's take a vector u. U is equal to, let's say, 2, -3. I want us to find the magnitude of u. So simple stuff here. I hate to say simple stuff, but it's really not. We've done much harder things in this class. So I'm going to take the square root of each of these components squared. So 2 squared plus sum of the components squared, -3 squared. So this gives us the square root of 4 plus 9, which equals the square root of 13. And that's it. That's the magnitude of the vector. So if you were to measure how long it is, it's square root of 13. Questions? Straightforward, yes? Okay, now definition, unit vector. Any vector that has a length of 1 is called a unit vector. So any vector that you ever have that when you take its length as 1 would be a unit vector. Here's an example here. If I take this blue vector, I can make it as long as I want to make it, right? Or short. No matter which way I point that blue vector, there's always some red vector that points in the same direction that has a length of 1. And you can almost see like a unit circle here around. That if I move this vector around, that red vector would have to lie, like terminate on the unit circle, right? So any vector, there's always a unit vector pointed in the same direction. Let me say that one more time. For every vector, there's always a unit vector pointed in the same direction. So how do you think we could find that? If someone gave us the blue vector and said, hey, go find the red vector. Wonder if anyone can figure this out. Let's say I give you a blue vector. Okay, I give it to you. Here it is, whatever. I give you the components. Maybe it's 2, -3 or something like that. Yeah, let me just use that. Let me say, here's u is equal to the vector 2, -3. We just did that problem right before this, right? And I asked you to find how long it was. The magnitude of this is the square root of 13. How do you think I could find this red vector? What would I have to do to the blue vector in order to make it become the red vector?
You'd have to shrink it.
I'd have to somehow scale it, right?
Mhm.
Shrink it down. How much do I need to shrink it down by?
Root 13.
By its own
Plus its
length. By its own length. If you were to scale it by its own length, then it would have a length of 1. So let's just say for the sake of making this easy, let's say that the blue vector had a length of 3. Wouldn't I need to basically scale it by 1/3 to make it 1? Or if the blue vector had a length of 10, I'd have to scale it by 1/10 in order to make it 1 unit long. So if that vector if we know that the length of that vector is square root of 13, then I need to scale it by 1/√13 in order to make it length 1. That's what the next note is about. It says, given any vector in 2 or 3 dimensional space, we can find a unit vector pointed in the same direction as that vector u by simply taking 1/, the length of the vector and then multiplying it times the vector. Another way of writing that is taking u and dividing it by its own length. So we'll just do that example that I just had. If u was equal to the vector 2, -3, and we know that the magnitude of that vector was the square root of 13, then a unit vector in the same direction would be 2/√13 -3/√13. So basically what we're doing is we're taking 1/√13 and we're multiplying it times the vector 2, -3, and that gives us this. Because 1/√13 is a scalar, and we do scalar multiplication by just multiplying each one by that, and we get this. Now, do
I
you
have a
believe
quick
that this is
question.
correct? What? Go ahead. What?
So could you say that you're multiplying vector u by the reciprocal of the magnitude?
Yes, that's exactly what you could say.
Okay.
Yep, you're multiplying it by the reciprocal of the magnitude right here. Yep. Now, do you believe this is correct? Do you believe that this vector has a unit length, has a length of 1? We could check it, couldn't we? What would the magnitude of that be? You would do the square root of each of these things squared, right? Add them up. So if I square that, I get 4/13 because the root goes away. Plus, and if I square that, I get 9/13. If I add those up, I get 13/13. And that's square root of 1, which is 1. So the length of this vector is 1. It works, all right? You just need to remember this, like Anna Marie said. You just take the vector and you multiply it by the reciprocal of the length, or 1/its length. Okay. All right, now we're going to talk about what are called the standard basis vectors in two-dimensional space. So there are two very, very important vectors, two really important vectors in two-dimensional space that if you take a physics class, you're going to see these vectors. They are called, we have a name for them. This first one right here, sometimes you'll hear that referred to as I hat, because it's an I, a bolded I with a little hat. He's wearing a little hat. And then this one is J hat. But at the end of the day, those two vectors are just two very special vectors, okay? They're just vectors though, okay? Let's look at the first one here, I. I is the vector that you go to the right one, and then your y is 0. So it's just the vector that points out right here like this, like that. That's I hat, okay? Now, what makes it kind of special is that it's a unit vector. Do y'all agree it's a unit vector? You can just tell by looking at it that the length of it is 1, right? Because it just goes to the right one, that's it. And then J hat is the vector that points straight up and goes up here to 1. It's also a unit vector, okay? Now, I know none of you have taken a class called linear algebra. You can only take linear algebra when you get to Cal 3. You can take linear algebra and Cal 3 at the same time. But in linear algebra, these two vectors form what's called an orthonormal basis for R2, which is a really fancy way of saying that, let me write the word down. You'll probably never see this again, but orthonormal basis. Okay, those two vectors create what's called an orthonormal basis for R2. Okay, ortho comes from the word orthogonal, and orthogonal means perpendicular. So do you all agree these two vectors are perpendicular to one another? Yes? Normal comes from the idea that they're both unit vectors. Okay, so this says we have two perpendicular vectors that both are unit vectors. And then the last word, basis, is what I'm about to tell you right now, okay? This is what makes I hat and J hat so special. So they're unit vectors, and what makes them extremely special is this. I'm gonna clear all this out of here. Is that if I take I hat here in green and J hat here in green, if I take any other vector, let's say I take any vector I want, here, 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 it doesn't matter where it is, I can always create that vector U by taking the I, scaling it by some number. So if I take I and I scale it, it's going to come out to here, right? Somewhere. If I take J and scale it, it'll come out here. And if I add those two vectors together, if I were to add this vector and this vector, I go tip to tail or tail to tip. And what would happen is, let's take this one and come here. Let's take that one, add it to this one. I go tip to tail here, and it would come up here, and it would give me U, wouldn't it? And that works for any vector that I could ever come up with anywhere in two-dimensional space. I can somehow write U can somehow be written as some scalar multiple C1 times I hat plus some other scalar multiple C2 times J hat. And that would work for any vector U. So what we say in math is that any vector in this space, any vector in two-dimensional space, U, can be written as a linear combination of I hat and J hat, which just means that we can just scale I hat by something, scale J hat by something, add the two vectors together, and we will wind up at U. Does that kind of make sense, everyone? You can get to any vector, any vector in the space by just somehow combining I hat and J hat together. So when I wrote orthonormal basis, ortho meant perpendicular, normal meant they were unit vectors. Basis means they create the whole space. You can create the whole space from just those two vectors. Okay. We're not going R3. We're not doing that. We will do a problem like this. Okay, so let's write, I want us to take the vector v equals, let's go 2, 3, and let's write it as a linear combination of the standard basis vectors. So here's how I'm going to write this. This is, tell me if you agree with this. This is the vector 2, 0 plus the vector 0, 3. So I'm kind of like reverse engineering this vector. 2, 3 is the same as the vector 2, 0 plus the vector 0, 3. If I added those together, I get this, right? But the first vector is 2 times 1, 0, and the second vector is 3 times 0, 1. So I'm kind of reversing scalar multiplication. I realized that I could like factor a 2 out of here and factor a 3 out of here. And then I'm realizing that 1, 0, that vector is just I hat. And then this vector over here, 0, 1 is j hat. So 2i hat plus 3j hat is this. Now, you don't need to show me all this work. Okay, you don't need to show me all of this. I'm just trying to show you like what it means. If you wanted to, like on a different example, if you want to say, okay, write this as a linear combination of standard basis vectors, you could just write negative 4i plus 5j and be done. But I think it's important to understand why. So this is what's happening here. Does anyone have a question on that at all? All right, we got to move on. We've got to move on. What's going on? Oh, you know what? I know what's going on. Okay, so let's now talk about finding the direction of a vector. Right now, if someone gives us a vector, we can find its length, right? We can actually find a unit vector in the same direction. But how do we find its actual direction? So we can go to a picture here, take some vector here like this. Let's call this vector u. We'll say it's the vector u1, u2. I'm using u instead of v just so that you're comfortable with it. If I want to know this angle, that's the direction. And I actually do know that this is u2 and this is u1. What can I use? What trig function connects u2 and u1 together?
I would use tangent.
Yeah, we can tell by this picture and what we've learned in pre-calc that tangent of theta would be u2 over u1, wouldn't it? It would be the opposite over the adjacent. So if you wanted to know what theta was, you could now do the inverse tangent on both sides. Right? Now, we have to be careful because we know already that when you use inverse tangent, that means that there's a domain restriction, right? This means that your theta, the answer you're going to get is going to be between pi over 2 and negative pi over 2. We know that there's kind of like weaknesses to the inverse tangent function. So on our calculators, we have to be careful. I'll show you an example. But that's it. That's how we can find theta. So let's do an example. find the direction of the vector u equals, we'll start simple, 4, 7. First thing I'm going to do is draw my vector. Just a real quick sketch of it. That vector goes out 4, goes up 7. And so here's my vector. I need to find this angle, right? I know that that angle should be equal to tangent inverse of the u2, which is basically the y component over the x component. And then I just get on my calculator and do this. I get approximately 60 point, let's say 3 degrees. Okay. That clear? Yeah. Okay, now let's do the same thing. I want us to find the direction of the vector u equals, how about 4, -7? So that's almost the same vector, except that I go out 4 and I go down 7, which puts me here, right? Like this. Yeah. So theta, see, this is a little weird because arctangent, we're not going to get an angle that goes anywhere over here. So this answer that we're going to get is this angle, isn't it? When we do this on our calculator. So theta will be inverse tangent of, careful, -7/4. And that's what, -60.3? Right? Oh, why didn't I give me these? There we go. Y'all, does that make sense to everyone? Now, could you give me a coterminal angle to that? That's a positive angle. Like maybe in a word problem, we're going to want a positive answer. So could you give me the angle that would be this one?
Yeah, it would just be 360 minus the,
Yeah,
or I guess plus
just
that.
do 360, take away.
Our original theta.
Yeah, exactly. So minus 60.3. So if we wanted a positive angle, we could say that theta is equal to 299.7. See, we don't have to restrict the domain. We don't have to restrict the domain in our answer. We only have to be aware of the limitations of the inverse tangent function on our calculators, that it's only going to spit out an answer between here and here. Let me give you one last example, and hopefully you'll understand what I mean here. So find the angle of the vector u equals -4, 7. So that means if my vector is to the left 4 up 7, it's this vector. And there's going to be a problem because this is in a quadrant that the arctangent's not defined. So when I do this inverse tangent of 7/-4, it's going to give me -60.3 again. See, because the calculator doesn't know the difference between these two. Do y'all see that? It doesn't know. This is -7/4. This is 7/-4. Those are the same numbers. So your calculator has no idea at all that we are in the second quadrant, not the fourth. Our calculator thinks that we're over here, which means that the calculator thinks that this is -60.3, when in actuality, we want this angle from here to here. So how can we get that?
By
You just-
adding 180.
Yeah.
You could add 180 to it. Yeah. Or you could also say, all right, well, you know, from here to here is also 60.3. And so this plus this has to be 180, which means you're going to subtract that from 180. So it's all the same thing. I do 180, take away 60.3, 119.7. So that's incorrect. 119.7 degrees would be our theta, our direction. Okay. All right. Let's see, we have about 9 minutes. Magnitude and subtract. I want to make sure I've covered everything. So unit vector. I want to do one of these word problem ones here. Okay. I'm going to just try and do one problem here. All right, so let's say we're looking from the top down, and what we have here is a plane. Okay, so an airplane. So I'm going to draw a little airplane here. It's going to be really a good airplane, I can tell already. That's an airplane. We're looking from the top down. There's a little cockpit and the wings, and wow, that's terrible. This plane is flying this direction, okay? Now let's say the plane is going, let's go 400 miles per hour. All right, and what I'm going to tell you is that the direction that they're going is 40 degrees south of east. In other words, if you were to draw like an XY axis here, this is north, south, east, west. It's 40 degrees south of east. So this right here is 40 degrees. Okay. And then I'm going to tell you that there's a crosswind, or let's say wind. I won't say crosswind. There's wind blowing at 80 miles per hour from the east. From the east. So that means the wind is coming in like this. Okay, the wind's going like that. 80 mile per hour wind. We're way up high. Okay, the plane's up in the sky, so 80 mile per hour wind's not that big of a deal. Okay, so the plane is aiming this direction. Okay, it's aiming that direction. The wind's coming in from the east. The question is, what is the true direction of the plane and its true speed? Relative to the ground. Now, I don't know how many of you have ever been in an airplane. If you've ever looked out the window of the airplane, you're sitting there. I don't know if you've ever seen, I know it's happened to me several times where I've seen a small plane somewhere below, and you're looking at it and it looks like it's flying sideways. Like it's not, it looks like it's going straight, but relative to the ground, it looks like it's moving like not straight. I don't know if y'all have ever seen that before, but that's what's happening. You have wind, you have the plane aiming in a direction, but the wind's making it do something else. And so it has it has some true direction and true speed, but the wind plays a role. Okay, so I don't know if I'm gonna have time to set this up. Does anyone have a question as to what's going on here? Like, no? Okay, so here's how I'm gonna do this. I have two vectors at play here. I have the plane itself, which is this vector right here. And I'm going to put 400 here, and that represents the length of this vector. And I'm going to call this vector P for plane, okay? And so the 400 is telling me that the magnitude of the plane, the magnitude, the length of the vector is 400. You cannot write this. This makes no sense at all. To write P, the vector P is 400 makes no sense because a vector needs two components, right? It needs angle brackets. I can only tell you that the length of the vector is 400. That will represent the speed. Then I have the wind, right? I want the wind to come in here as a vector. And that wind should point in that direction, should have a length of what? How long should that vector be? 80, because again, the wind speed is 80. So I know that if we call this W, then the magnitude of W is 80, okay? Now that wind vector is everywhere, isn't it? So what I'm gonna do is I'm going to add it to the plane vector and to see what the result vector is gonna be. So I'm gonna take this vector and I'm gonna move it here. Now I could have moved it over here too. Doesn't matter. I could put it here or I could put it here, but I want to add the two vectors together. The resultant vector is the vector that goes from the tail of the first vector, the plane vector, to the tip of the wind vector. I totally missed it. To the, shit, that's terrible. I'm not gonna be able to do this. Oh, it's just a weird angle for me. Try it that way. Okay. This is going to be, I'm going to just call this vector T for the true result of what's happening. So does that vector make sense? If you're pointed in that direction and you have wind coming this way, the wind should shift the plane to not point here, but to be going this direction, and it should slow it down. This green vector is going to be shorter than that vector. So how can I find out the answer to this? What is the direction of the plane? So what angle do we need? And there's a couple of ways to look at it. Could I find this angle right here? That would be enough, wouldn't it? That would give me the direction of the plane. And do we know this angle right here?
40.
40, okay, degrees. And so I know that this angle will be, well, shit, if I just had that angle, right? If I had that angle, let's say it was 5 degrees, then this would be 45 degrees. Then I could figure out the rest, right? Yeah. Okay. Man, can you figure that out? Are y'all starting to see this? I'm really hoping you're starting to see this. This is 400. This is what? What's the length of this one?
80.
80. And then this one that we're looking for here, the length of that vector T would be how fast it's going, right? At the true speed would be how long this side is. And this angle theta will help us get the direction of the plane. Are there any other angles you know? I have to end class. This is not enough to solve this triangle. Are there any other angles you know? There's one. Do you all see it? look at this here. See that angle here? Maybe I should just throw this out here. If you have two lines that are parallel, this is a geometry thing you may or may not remember. If you have a bisector of two parallel lines, this angle has to be equal to this angle. Also, this angle has to be equal to this angle. And the one across from it has to be the same. So the one across here has to be the same. And the one across here has to be the same and the same. So what you need to see here is that if you have this line and this line, okay, like that, do y'all see the red line comes through here like this? That angle should be equal to this angle right there. Those two angles should be the same. We call these alternate interior angles. It's basically this one and this one. So that tells you that this is 40 degrees. And now you can solve this triangle. How?
You can use the law of sines.
Sines or cosines or something, right? I've got to end class. Okay, so I don't know what the homework's going to look like for this section yet. I'll go do it and do my best. Hopefully what I've done here today will fall in line with the homework. I have a feeling there might be some notation differences, but for this problem, I'd say just try and finish this on your own. We'll come back and finish it next week. Okay, everyone, have a good day. I'm going to take off. I've got to go check. What's that?
Yeah, hope everyone feels better.
Thank you.
Yeah, me too. We're going to find out if she has COVID or not. So we'll see. Okay, y'all take care.
Bye. Have a good weekend.
Sure.
Bye. Thank you, sir.